Good day. We are from Group 5 and today we are going to explain Experiment 5 bending moment. Our group member consists of Hervin, Ganesh, Subhatra, Vika and myself, Teotun Seng. So we are from section 5 and our lecturer name is Dr. Siti Haja binti Cheman.
Hi, my name is Hervin Kwan. First of all, I will explain on the abstract part of the experiment. The experiment 5 was conducted with the objective to measure the bending moment of a material. In order to conduct the experiment, some methodologies was followed. First, an experimental beam, which consists of smaller and larger part, was connected by joint to form a frictional hinge. Then, 3 load hangers are placed on a beam. Some loads was later loaded into the hangers. Finally, spring balance on the beam was used to adjust the beam when the beam is bending. From the experiment, we obtained the results that confirm the theoretical claim and thus confirming the bending moment theory. We also reached the conclusions that bending moment varies with positions and mass of loads on the material.
Next, the objective. The first objective of this experiment is to measure the bending moment at the normal section of a loaded beam. Secondly, it is to compare the obtained value with theoretical value. Thirdly, it is to study the definition of the bending moment theory. Next, theory. The theory used for this experiment was the concept of bending moment. So, first of all, what is bending moment? Bending moment is the torque that keeps a beam together, or also can be defined as a force that causes something to bend. So, how do we measure bending moment? To put it simple, it is force multiplied by length. We calculate bending moment by cutting the beam, then calculating the algebraic sum of the moment required of all the forces that are acting in one side of the section, either left half side or right half side, to hold the beam stationary. There are two sign conventions used for bending moment. The sign convention used are positive bending or negative bending. Positive bending is indicated by sagging bending, whereby compression is in the top fiber and tension is in the bottom fiber. Meanwhile, negative bending is indicated by hogging bending, whereby tension is in the top fiber and compression is in the bottom fiber.
Now, I'll explain about the bending moment with shear force. So first, consider a cantilever beam acted upon by a vertical force P in figure A. So now imagine that the beam is cut through at a cross-section XX in figure B. From the left-hand part, part A, the shear force Q in figure B with a blue box and a bending moment in figure C with a red box are assumed to be positive in the direction as shown in the figure B. And C, respectively, for vertical equilibrium of part A, there must be a shear force Q acting as shown in figure B, blue box, and equal to Ra. So for vertical equilibrium of part B, the shear force Q evidently acts as shown and has the value of P minus Ra. So we can assume the shear force Qx and the bending moment as a positive direction. So to calculate equilibrium part A, we can use equation mx equal to Ra times A. Equilibrium for part B is mx equal to Rv times B minus P in bracket B minus I.
Methodology, apparatus, and procedures. For apparatus, there are three types of apparatus that used in this experiment: beam, loads, and load hanger. This beam divided into two parts and connected by the fixed joint. This beam is 0.9 meter from the left hand to the right hand side. The spring balance is attached with the beam with level up of 150 millimeter. This is used to measure the force applied. There are three load hangers, P1, P2, and P3. Also, we use three weight of loads, 10 Newton, 5 Newton, and 2 Newton in this experiment. Procedures. For this experiment, it was divided into three parts, part 1, part 2, and part 3. For part 1, first, the experimental beam was set up as shown in this figure. And second, align the two parts to adjust the spring balance by turning its knot until the bubble of spring balance at the center and record the initial reading. Third, hang a 10 Newton weight on P1 and realign the spring balance and record the new reading that indicate the effect of 10 Newton weight on the beam. Next, the above procedure was repeated at P2 and P3. And finally, the whole procedure was repeated by using a 20 Newton load at P1, P2, and P3. For part 2, first hang 5 Newton weight on P2. The beam was aligned and record the reading of the spring balance. Next, place tool of 10 Newton weight at P1 and P3 respectively, and 5 Newton load was hung at P2. Balance the beam each time after the load is altered and record the reading of the spring balance. For part 3, first, the load hanger at P3 was indifferent compared with part 1 and part 2. Second, align the two parts to adjust the spring balance and record the initial reading. And next, a 5 Newton weight applied at P1, whereas a total of 12 Newton weight was hung at P3. And realign the spring balance and record the new reading. And the last, a 5 Newton weight applied at P1. 10 Newton load was hung at P2 and 2 Newton weight was applied at P3. The beam was aligned and the reading of spring balance was tabulated.
I'm Jun Seng and I'll explain the result of this experiment. For part 1, the table 1 shows the data for bending moment at C for the log configuration in part 1. So we can say the Y component and the moment at B is equal to 0 since it is equilibrium. So from the free body diagram, so when P1 is equal to 0, the Y resultant will be RA plus RB equal to P1. So this is equation 1. So for moment at point B is equal to 0, so we can get RA is equal to 8.89 Newton from the calculation above. So this is for equation 2. After this, we substitute equation 2 into equation 1. So we will get RB is equal to 1.11 Newton. So to calculate the moment at point C for the theoretical value, so we can use the calculation as shown, and after this we can get the value of 667 Newton millimeter for theoretical value. For experimental value for moment at point C, so from the table, when the load is 10 Newton, the balance reading is 25, while the initial reading is 20. So we use the 25 minus 20 Newton and we get the net force is 5 Newton. After this, we use the net force to times with the length 5 times 150 and we will get a value of 750 Newton millimeter. For part 2, when P2 is equal to 5 Newton, the Y component and the moment at point B is equal to 0, which is in equilibrium. So for Y component, RA plus RB is equal to P2 for equation 1. So for equation 2, RA is equal to 3.33 Newton after we calculate the moment at point B. After this, we substitute equation 2 into equation 1. Then we will get RB is equal to 1.67 Newton. So to calculate the theoretical value for bending moment at point C, we can use the equation as shown in the diagram, and then we will get a value of 999 Newton millimeter. So to calculate the experimental value, so from the table, we can see P2 is equal to 5 Newton and the balance reading will be 26. Then the initial value for balance reading is 20 Newton. So we minus this both value, we will get the net force is 6 Newton. So we will get this value and then 6 Newton times 150 millimeter, then we will get the value of 900 Newton millimeter. For part 3, so from the free body diagram, when P1 is equal to 5 Newton and P3 is equal to 12 Newton, so the Y component and the moment at B is equal to 0, which is in equilibrium. So for Y component, the equation will be RA plus RB equal to P1 plus P3 for equation 1. So for equation 2 for bending moment, we will get RA is equal to 9.78 Newton for equation 2. After this, we substitute equation 2 into equation 1, then we will get the RB is 7.22 Newton. So to calculate the theoretical value for bending moment at point C, so we use RS times 300 minus P1 times 200, so the value will be 1934 Newton millimeter. To calculate the experimental value for bending moment at C, so from the table, we can see when the loading is 5 Newton for P1 and 12 Newton for P3, the balance reading is 33 Newton and the initial reading will be 20 Newton. So we will use the final weight reading minus the initial reading. We will get the net force is 30 Newton. So we use the 30 newtons net force times 150 millimeter of perpendicular distance. We will get the final experimental value of 1950 Newton millimeter. So we will use the same calculation method to calculate the remaining data for part 1, part 2, and part 3. So this is a graph for part 1. So this is a graph for part 2 and graph for part 3.
I will continue with the discussion part. Based on the theoretical value obtained from part 1 of experiment, it shows that the bending moment is directly proportional with the load added. When the load is double, the bending moment is double. The relationship between the stress, bending moment, and load is that when the load increases, the stress increases and make the value of the bending moment increases. Therefore, the ratio of the increase in bending moment value is relative to the load. As stated in table for part 1, the bending moment and the theoretical value are almost same. When the load P1 equals to 10 Newton is applied, experimental bending moment is 750 Newton millimeter, while theoretical bending moment is 667 Newton millimeter. When P1 increases to 20 Newton, experimental bending moment and theoretical value are 1200 Newton millimeter and 1334 Newton millimeter respectively. When P2 and P3 is 10 Newton, the experimental bending moment are 1800 Newton millimeter and 900 Newton millimeter, while the theoretical value is 2000 Newton millimeter and 1000 Newton millimeter. Besides, the load applied at P2 and P3 is 20 Newton. The experimental value of bending moment is 4050 Newton millimeter and 2100 Newton millimeter, while the theoretical value is 4000 Newton millimeter and 2000 Newton millimeter. So, the bending moment did not double exactly as theoretical when the load was double is due to few factors. Firstly, there is a parallax error when taking the reading of the scale on the measuring instrument, which is the observer's eyes do not look perpendicularly to the scale on the measuring instrument. This leads to the inaccuracy in the data obtained. The next factor is because of the surrounding environment where the experiment was carried out. The experiment is carried out under the fan. The movement of air due to the fan will cause the whole system to become less stable, causing the data obtained to be inaccurate. The graph shows that the bending moment varies with the position and mass of load. Based on the data collected, an average percentage error expressing the comparison between the experimental and theoretical bending moment was calculated using the formula. We can observe that the percentage error for the experimental errors are relatively high, with 19.12% being the highest and 0.83% being the lowest. A large percentage error has shown to us that the experimental data differ a lot from the theoretical value calculated. This has indirectly indicated that the experiments was not conducted accurately, as errors may occur and precautions were not being taken. So there are some errors and precautions in the experiment. First error is parallax error. Parallax error occurred due to relative position of the observer's eyes to the scale. Hence, make sure that the level of the observer's eyes is perpendicular to the scale of the measuring cylinder when taking the reading. The movement of air at surrounding may affect the equilibrium of the beam. Make sure that the fans in the laboratory should be switched off upon carrying out the experiment. Other than that, the hanger position might change when the adjustment was made to the beam. Thus, make sure the position of the hanger is correct every time after the adjustment has been made. Lastly, the equipment may not be sensitive to minor changes in weight applied, causing inaccurate readings obtained. Hence, use more sensitive and precise equipment to improve the accuracy.
Finally, the conclusion. From the experiment, it can be concluded that the theory was verified such that the shear moment and bending moment increases with increasing amount of load which put on a beam, although the results obtained was with slight discrepancy between the experimental and theoretical bending moment, with the highest value at 19.12% at the load configuration part 1 and the lowest value at 0.83% at the load configuration part 2. The high value of percentage error was most probably caused by unforeseen errors and mistakes which was performed during the experiment, which was explained in the discussion part.
References: Thank you.